In this video, we are going to go over inflection points and concavity. And so we first should talk about what those are. So inflection points occur when the concavity of f of x changes. Oops. And so a function is concave up when the graph looks like part of a valley, and then concave down when the graph looks like part of a hill. So on this graph, we would say that this section right here, because it looks like it's part of a valley, this is concave up. And then the part after this point, it looks like now part of a hill. So I would say that this is concave down. And then this point where it changes is called your inflection point. It's also sometimes referred to as the point of inflection, so as long as those two words are in there somewhere. And that is because your original graph changes one way or the other. It could also change from going concave down to concave up, and then there would be an inflection point there as well. It doesn't necessarily need to go in this order, just wherever your concavity changes. To find inflection points, what we look at is the second derivative of a function. So first you want to find f double prime of x. Then you want to set it equal to 0, or you want to see where it does not exist, and solve for that x value or x values. Then you want to make a sign chart, and there are some conclusions we can come to. So if f double prime of x is positive, so anywhere that's true, then we would say our function is concave up, our original function. Anywhere where the second derivative is negative, the original function is concave down. And then anywhere that you have an x value, you have to check and see, in order for x to be an inflection point, your second derivative must change signs. So on a sign chart, sometimes you could end up with like a couple of x values, x1, x2. And this might be positive, this might be positive, this might be negative. So these are possibilities for points of inflection, or for where your inflection points would occur, but the only one that actually results in an inflection point is this one, because it changes signs from positive to negative. x1 would not be a point of inflection, or at least we couldn't justify it this way. So make sure it's not just every point where your second derivative equals 0. You have to do a sign chart and see where it changes signs. Then in order to find the point part of it, you have to, so to find the y-coordinate, you still need to plug x into your original function, because we're being asked to find the whole point, not just necessarily where the point of inflection occurs. So let's go ahead and try it. All right, so here is our first example. So we want to find the inflection points of this function, which means the first thing we need is my second derivative. So this will give me 12x to the third plus 6x squared minus 3. So that's my first derivative. My second derivative is 36x squared plus 12x. And then I set it equal to 0, or see where it does not exist, but this exists everywhere because it's a polynomial. Factor out of 12x, it looks like. And then you want to find your solutions. Remember, when we find our solutions, you're just figuring out where both of these things equal 0. And so if I solve that, I get x equals 0 still, and then on the side, x equals negative 1/3. All right, now I go ahead and make a sign chart with those values. And I'm testing things. Let's see, I'm trying to see if my second derivative is positive or negative, so make sure that this is for your second derivative. So I'll test -1, I'll test -1/4, and then I'll test 1 to see whether or not you end up with positive or negative intervals. And remember to test them in your factored form to see whether or not you end up with just positive or negative numbers. We don't actually care about the numerical value itself. So if I test -1 in here, I would get a negative times, see, -3 plus 1 is a negative, so negative times a negative is a positive. Okay. If I plug in -1/4, I'd end up with a negative number times a positive number, so that one would end up being negative. Then if I plug in 1, I get a positive number times a positive number, so that ends up being positive. So we would say that both -1/3, or x equals -1/3 and x equals 0, produce a point of inflection, and then we actually just need to find the y values of those. So I'll find f of 0 and f of -1/3. F of 0 is easy, we get 0. F of -1/3 is a little bit trickier, but if you want to practice your arithmetic on it, you can. You should end up getting 26/27. So that means I have points of inflection at 0, 0, and then at -1/3, 26/27. You could say result, or R, points of inflection. And then if we practice our justification for that, we'd say because f double prime of x equals 0, and changes signs at these points. It's not enough that f double prime of x equals 0 there. It also, you have to include the changes signs portion. So it didn't ask us to justify our answer in this, but I figured it's always good practice. All right, let's do another example. So in this one, it says find the points of inflection and determine the change in concavity at these points, or at those points, if f of x equals this function. So we're still going to follow the same setup as what we did in example 1. And then we're just going to talk about how it actually changes concavity. Does it change from positive concave up to concave down, or vice versa? And so let's do it. F prime of x is 12x squared minus 4x plus 10. F double prime of x is 24x minus 4. Set that equal to 0 to solve for our possible point of inflection x value. I get x equals 1/6. So I'll do my sign chart. And I'll test 0 and 1. All right, if I plug in 0 here, I get -4, so negative. If I plug 1 in here, I get a positive number. So we can say that, in fact, yes, x equals 1/6 produces an inflection point. So we'll go ahead and we'll find that y coordinate by plugging 1/6 into our original function. And when I do that, I end up getting 44/27. So that means that I have an inflection point at 1/6, 44/27. And then if I'm talking about my change in concavity, we would say that for all x values less than 1/6, my f of x, my original function, is concave down. And then for x greater than 1/6, my original function is concave up. So at this point of inflection, my original function changes from concave down to concave up. So it should look something like this, and then it changes to something like this, and you'd have a point of inflection there. Awesome. All right, so that's it for this video, and then we'll go over the last little part in the next one.